So this is a short presentation about the NESSI project in Norway. NESSI stands for Norwegian Environment for Scientific Software Installation. It's a project funded through Sigma 2 and NRES. Sigma 2 is the national provider for infrastructure in Norway. So you can think of HPC and storage. NRES stands for Norwegian Research Infrastructure Services, and it's basically a collaboration between Sigma 2, NTNU, UAB, UIO, and UIT. So the four universities in Norway, and they're depicted on the cards, so you know where they are. And NESSI has, let's say, similar goals to EASY. It was launched in September 2020, and also has some history dating back from that. So what you see here, so in Norway, we have a long history in running CERN WMFS for the Nordic Data Grid Facility Tier 1 Center. That's a distributed Tier 1 Center for the worldwide LHC computing grid. And in that, we have experience running this on physical and virtualized setups. Another thing we did, also predating the NESSI project, is we had an exploratory project on extending HPC with cloud resources in 2019. And the idea there was that, let's say, the queue is full on HPC, can we add resources from the cloud and make it such that the users don't notice this? And then we worked on a proposal for a national infrastructure for artificial intelligence. And the same time frame, 2019, 2020, and there we had the idea that users should be able to nearly seamlessly migrate their workloads between different resources. Let's say they start on their laptop, then go to a group server. Maybe then they need more resources. They go to the university infrastructure. And if they even need more, then they could go to the national infrastructure or international infrastructure. And they're having something like EASY, of course, would be very helpful for them. Then the actual NESSI project started with a pilot phase, and there we wanted to investigate more CERN WMFS and how to use feasibility on that. Pilot phase started in September 2020, ran for about 6 months, a bit more than 6 months, actually, maybe more like 7-8 months. From the start, because we already knew about EASY, and we already had contacts with EASY, so we close collaboration with them, and we tested the pilot. We set up a Stratum server for EASY. And then towards the end of the pilot phase, the conclusion was to suggest that we move forward with that, and that we maybe have a development phase of 1 year, then afterwards development phase 6 months, and then go into operations. In that time of the pilot phase, we also made wrote a proposal called Scientific Software Stacks as Service S4, and submitted this to NAIC open call in March 2021. NAIC stands for Nordic Infrastructure Collaboration. The basic goals of that proposal were to bring EASY to the Nordics, Baltics, and putting in experience knowledge from key contributors to EASY. Then the development phase, the main goal of that was to help make EASY ready for production. It started in May last year. Originally, it was planned to last 1 year, but now we expect it to end maybe this year, by end of this year. And on paper, we had about 2 full-time employees for 1 year. And in reality, we had maybe about 1 FTE, because many people have other projects to work on. And so, yeah, delays are expected, I would say. Yeah, and also in the beginning, we had, let's say, a wide variety of tasks, and maybe that was not really good to focus our limited efforts, and so over time we concluded we look more closely what EASY really lacks to get into production or closer to production. At the moment, we really focus on this semi-automatic procedure to build and deploy software. However, we do not expect that the development ends in December. Clearly, so that we have learned, I would say, maybe we knew this already before. But we think that by December this year, EASY should be able to build larger stacks, software stacks, and then we could also, let users actually explore them and then try them. Actually, we have the EASY pilot available on our system, but we don't make it. So we also submitted a renewed version of this S4 proposal to NICE's open call early this year. Just a bit of motivation. This is actually a slide from the EASY user meeting early this year. So you just see some different phases like development, deployment, production, and the motivation from our point of view is that we would like to change how we provision software on the next HPC system. We would like to make it also available on the existing system, but we don't expect that we change the default way how software is provided on our existing system. And if you see in the timeline, the design of the next Norwegian HPC should be known early next year, maybe mid next year. And it should go into production then early 2024, maybe mid 2024. And of course, we would hope that then EASY could be the main or default software stack. Some future ideas to beyond bringing EASY to the users on national HPC systems in Norway. We could think of bringing EASY to actually everyone in Norway. Yeah? So, and of course, we could not do this with the current level of funding we have or the team we have. So we would need to see what other funding schemes we could. And then another idea could be to provide data science, research data management tools to everyone. So having all the necessary tools you need for data science, let's say, or research data management in the stack there, then you could use it on your laptop, on your HPC, and so on. It might be a useful thing. I think yesterday there was some discussion about the compatibility layer, and on the right, lower right, you see how I see a bit the architecture of EASY. Yeah? So you have in the middle, you have this compatibility layer, and on top you have the applications there, and on the base you have all the different architectures, CPU architectures, and this maybe you notice it. It's also known as the hourglass model. And what I sort of have in mind maybe for a future, it's really just a vague idea, is one could maybe try to augment the applications with functionality via this EASY compatibility layer. And if you have, if you do this, then this becomes then transparently available to all applications, to all users. And it could be something interesting, but I don't know what to use it for at the moment. So I think that's all I wanted to say. If there are questions, then I'm happy to answer questions.
Any questions in the room or on Zoom?
No question. Maybe Thomas, you can briefly say something about S4 as well.
I think the results should be known soon. But
yeah, so S4 is another project proposal focused on the Nordics, where we're asking for funds from the NAIC, what's it called, foundation organization?
Nordic E-Infrastructure Corporation. It has a similar funding model like Euro HPC joint undertaking. So 50% comes from NAIC and 50% comes from partners. So I would say the bulk of the effort is allocated to partners in the Nordics, like Norway, Sweden, Finland, and Estonia. But then there are also other partners like in the Netherlands, SURF and University of Groningen, and University of Ghent, University of Brussels, I think, is also in Belgium a partner, and CERN and CSDS are also partners. Well, yeah, they all know certain pieces of EASY quite well. They have competence in it. So the idea was there to bring them in so that we don't have to reinvent the wheel in the Nordics and also benefit from their experience and knowledge.
So that's currently under review, so we don't know the results from that yet. And that's sort of a follow-up to NESSI, right?
Well, it's widening the scope, I would say. So NESSI is only in Norway and has
and this is for the Nordics.
Nordics.
So we'll see how that goes. So maybe more good news on funding coming up soon. All right. Final round, final chance for questions to Thomas on this.
Stefan raised the hand.
Yeah, then I guess we can switch to Stefan Allen straight away. He's on the call already.
Yeah.
For NLPL.
Yeah. Okay, so Stefan, do you want to introduce yourself, or should I say a few words?
I was actually going to ask you a question, but we can take that offline, I guess. Within Norway. And I'd be happy for you to introduce me. Yes.
Yes. Okay. So I know Stefan for quite a long time. I think maybe since 2014 or so. And at the time I was working for NAIC actually, and he had the idea to build up a laboratory for researchers working with language technology. And we had the NAIC project, and I think he can talk about that and what they learned with EasyBuild and what their plans maybe are.
Okay, thank you very much. Thanks for having me today. I was a little curious to catch up with current state of play in EASY because I think it's an exciting initiative in the right spirit. I am ordinarily a professor in natural language processing at the University of Oslo in the computer science department. Natural language processing is developing the methods at the core of things, services like Google Translate or Siri, that is software systems that do something resembling natural language understanding, that to some degree make sense of our human. So natural language here means human language, Norwegian or German or English. And so this is a brief reflection on this initiative that we started 6 or 7 or so years ago, which is an attempt to organize our community of researchers in natural language processing, NLP, or human language technologies. Those two are more or less the same discipline. It's a network of university research groups in NLP, primarily in Scandinavia. We're currently joining forces with Edinburgh, I guess that's Nordic too, and Prague. So it's becoming decreasingly Nordic and more European, maybe. That has gained, happily, some support by the national infrastructure, the HPC providers in Finland and Norway. And the overall goal is to enable all of us to find the same working conditions, the same environment on multiple different national clusters. And currently we're fairly excited to be invited into the Euro HPC Lumi pilot. So we're currently compiling our software there. And essentially it's about maintaining discipline-specific software, also data, but I won't talk much about that here. Ourselves, because the software we use and develop is discipline specific, it's specialized, and often we find that we are at least as well suited, equipped to tune it, to optimize it for a specific system, to maintain it, as are the core system support teams. So mostly an infrastructure for collaboration across universities, to some degree a self-help initiative across borders. And the most interesting part here is this notion of the virtual laboratory. So we should be able to meet on a national cluster or on Lumi and all find the same software and data environment, the same set of modules. And to us, modularity, interoperability, uniformity, and reproducibility are key. So the way we approach this has to be sort of informed by these values. And a lot of current NLP software development from the sort of researcher's point of view is through Python. And Python, as many of you probably know, is, let's say, a very dynamic, fast-moving software environment. And there are many versions we need to cater to. So the researcher has their own code, and it builds often on a deep learning framework like PyTorch or TensorFlow or JAX, which for a specific version of PyTorch often is dependent on a specific version of a set of NVIDIA tools or AMD tools. And then below that, there may be specific requirements on whatever Python 3.7 something, and possibly even a specific version of NumPy. And that cross-product means we have a potentially large number of modules to maintain and provide. And to some degree, our philosophy is to give the researcher much say, not to tell them, well, actually, you have to make this work in Python 3.8 or this version of PyTorch. We try to meet them where they think they need to be. And to address this goal of uniformity across different systems and reproducibility, automated software installation obviously is a necessary tool. And since for the past 2+ years, with support from EOSC Nordic, we have developed a repository, a collection of easy configs, of easy build recipes. But we find it difficult to parameterize. So there is a specific system hardware configuration with possibly vendor-specific pieces of software. And we find it difficult to strike a good balance in building on what is there and what we think is best maintained by the sort of HPC staff, and building on top of that. So on a cluster where EasyBuild is the default tool for software maintenance, that problem is greatly reduced. But on a cluster where that is not the case, we either end up duplicating a large number of system-provided modules, if we just sort of run our stock repository of easy configs, or we need to sort of cut somewhere in that dependency tree and make adjustments. And part of that challenge that we still find a little difficult to navigate is there are third-party dependencies. There are the NVIDIA. Most of this is on GPUs. Multi-GPU, multi-node support is important. So things need to hang together properly. We currently share across these systems a collection of essentially binary archives, for example, for CUDA and the CUDA deep learning libraries and cross-node communication libraries, NCCL, and something parallel now on the Lumi system, which has AMD GPUs for the ROCm ecosystem. So RICL is the AMD replacement, parallel twin project to NCCL. But that means that we essentially we bifurcate our collection of easy configs and suffer from that cross multiplication. Why is this important in an HPC context? Natural language processing is increasingly about scale. So this is a graphical view on what are called very large language models. You may have heard about BERT or GPT. These are these very large pre-trained language models. They're at the core of any service, any product you meet nowadays that does something about language. So spell or grammar correction or translation, text prediction, what is the next word while you're typing a short message. Essentially, any editor that gives you some feedback on the text as you write it has at its core one of these very large language models. And here we see their evolution in size. So the original BERT, released by Google in 2019, I was going to say, but October 2018, yes, had a dramatic impact on natural language processing. And since we've seen an evolution of increasingly large models. So as of May 2022, we're looking at a model, sort of largest available model, has, what is it, 300 billion parameters, depending on what you think about what floating point precision you need. That can be a terabyte of GPU memory. And decades or centuries of GPU time to actually train such a model. And we see here that this space is dominated by Google, by Facebook, by NVIDIA on Amazon or Azure, OpenAI. So this is a space dominated by corporate players, and for university research to democratize that research space, to level the playing field, it's very valuable that we actually can make effective use of a system like Lumi to continue to do cutting edge or more contemporary, modern, state-of-the-art research in this space. In part because we think it's important that research continues in the open university space. In part because the tech giants inform their development focus by commercial interests. They are far less interested in a language like Norwegian than they are in a language like English or Chinese. Okay, so that was so currently we're not building on Easy, but in principle, I think we might want to. But we are active users of Easy Build on the Lumi system. The current support policy is actually possibly informed by this NLPL experience. I don't know that for sure, but it looks as if that may be the case. So the other philosophy is to actually give more of the software maintenance responsibility to user communities, and the sort of core module collection is built by EasyBuild. And the goal is to have a repository of contributed easy configs and also train disciplines, individual user communities to build on top of that by maintaining their own discipline-specific collections of easy build recipes. And by and large, that has been, from our point of view, a successful enterprise. So we have this virtual laboratory now on 4 national clusters with more or less the exact same collection of modules in the exact same versions and the exact same names, providing the exact same behavior. And that means that researchers can just migrate and choose a meeting place where they can actually both get access and allocations more freely than used to be the case. Okay, thank you.
Any questions for Stefan?
Maybe one question. Do we also use the same modules on non-HPC systems like your laptop or servers?
No, currently we don't. But there is very little development actually. So I think most of the researchers in this space, so we bring in master students actually in master teaching already into the sort of the university cluster, and there they meet the same environment, and then if they need to, as part of their master's thesis work, let's say, or if they advance to a PhD project where they need more than, let's say, a couple of GPUs, then they migrate to a national cluster. And we're, as a department, reducing, maybe even phasing out sort of standalone servers. So as a department, we have invested in additional GPUs as part of the university cluster. We're trying to reduce computational islands. And that means that this uniform software environment is available where most of the work happens. I don't think there's any of our users who actually does the work of running the compilation of our easy recipes on their laptop. In principle, I think they could, but I haven't met anyone who felt the need to do that.
Okay.
Well, and actually, no, they couldn't, because they would need the sort of collection of those binary archives and all their GPU. There isn't that much that they can actually do without availability of a GPU.
Okay, thanks.
Well, I have a small question about, let's say, hopping from NESSI to Easy. Is the experience you got from working with CVMFS also contribute to, let's say, the choice of sticking to this platform and getting Easy on track? Your experience with CVMFS, how was that?
That was the question put to me, I guess.
Oh, I hear it. Yes.
Yeah. So I would say that we just have some in-house experience, at least at two universities, because they operate part of the Nordic Tier 1 Center for high energy physics. So I don't think we have considered any other alternatives. So it's more the other way around, because we already have experience. We considered it CVMFS already at the starting point for NESSI, even before knowing about Easy. So yeah, it's more the story. It's always more like that.
Can I
Okay,
comment
thanks.
on that, actually? So there is actually a connection here, I think, between the NESSI work and our NLPL virtual laboratory, because that virtual environment also includes data, specifically these pre-trained models that we don't want that each user duplicates in their project space or home directory. And so we also have a need to maintain a uniform collection of data. Currently, we're rsynching from cluster to cluster. And we've discussed with NESSI the use of CVMFS for that purpose. We've talked about a pilot that we haven't initiated yet. And so in as much as that infrastructure takes foot, if Sigma 2, the national Norwegian provider, actually, I think you said, Thomas, they're expecting to migrate their software stack on future national clusters to be Easy based.
I would hope so.
It would be tempting to suggest that infrastructure also somehow caters to this need of a community sharing data across these clusters without manually copying it from system to system.
Yes.
How big is this data you're referring to? Is it
Oh,
gigabytes,
it's
terabytes, petabytes?
No, it's tens of terabytes.
Yeah, we saw talks at the CVMFS workshop where they're literally juggling petabytes, sorry, through CVMFS. So anything in the order of terabytes should be very doable.
Yeah.
Yeah. And I had another question. Yeah. Go ahead.
I think that when we discuss it, it's more the question of sort of injection path and tiers of maintenance responsibility.
Yeah.
Janet, you had a question?
Metadata.
That doing that kind of data sets was using external files, so more using CVMFS for the hierarchy instead of the actual storage and surfing.
Yeah, it's indeed a two-layer thing. And I did have another question for Stefan. So all this effort you have to do to get the software installed, to build these easy configs, juggle all these dependencies, do you see that as a necessary evil that's really part of your research, or do you say, why the hell do we need to take care of this, and why is this still such a big issue?
Well, I mean, it's the choice between hassling a system administrator who has no knowledge of natural language processing and
I know time to fight.
Limited knowledge of the deep learning frameworks. So, I mean, PyTorch, TensorFlow, those are not discipline specific, but they are specific. They're the tools of choice for disciplines that don't have as long an HPC tradition as theoretical chemistry or climate research, maybe. So we actually found it enabling. I mean, we need to be very knowledgeable of our own software, which builds on top of that software stack. And it's, I think, overall, it increases sort of technical competencies within our community and reduces friction at the interface to the core HPC system maintenance.
And is this
we welcome the extra effort, I think.
And is this an issue you see getting worse? So with more, like, I guess the community is largely moving to PyTorch, but then JAX is also becoming interesting. And is it going to get worse? You'll have to juggle more things in the future, or?
I mean, there's a growing research community, right? And things move very fast. And so that means someone might be interested in building on this third-party code that came out of some Facebook lab, or could be a Chinese university for that matter. And as the research field grows, probably also the diversity and software stacks that people would like to use grows. But I think that's a manageable growth factor. At the same time, as you indicate, I think there may be a time in the foreseeable future where TensorFlow can be left behind.
Mm-hmm.
And JAX actually is becoming more important, yes.
It's sort of replacing TensorFlow, yeah. And just one small piece of advice there, do not take the example of, or do not take bioinformatics as an example of where you need to go, because there it's just a gazillion tools and it's an absolute nightmare to get all of them aligned and working. So don't go that way. Okay. I guess we're ready to switch to the next side talk, Danilo. So we'll need to do some reshuffling there. Thanks a lot, Stefan and Thomas.
Yeah, thanks a lot, Thomas.
Yes. Yes. Okay. Well, so today I want to talk about a little bit about some solution that we just figured out for one of our clients. This I call it a tailor-made distributed app stack. So to start, a short introduction about the HPCNow. So we are a high-performance computing focused company. So we do all the whole package, meaning we plan, we install, and we support. So we in the planning phase, we can provide solution design adapted to the users. And in the solution installation phase, we provide infrastructure, software, training, all the things that they need to use it properly. And in the maintenance phase, we provide support and also manage their services. So as I pointed out at the beginning, so they want to explain a little bit about this use case. So this is the example. So we have a pharmaceutical company that have different clusters with different architectures managed with different organization around the globe, and they want to have an app stack that works in every place. Also, they want to use this app stack in the cloud, and they want to use it in the laptops and workstations. So I think that is the general feeling here, that something that works everywhere and without difficulties for the researchers. So it's like the ring to rule them all. So it sounds like a ideal case for easy, but this kind of companies have some restrictions. So the first one is they commonly with their software, they have a self-developed databases that is quite restrictive. I mean, they develop and they cannot distribute it. It's not open. So this one case. The other one is they have restricted custom or internal developed software. So the same case of the databases, so cannot be distributed. And they have a lot of security concerns. I mean, they want to have total control about the software that they are using. So it's not up, well, at least not now, it's not available to use open, well, wide distributed app stacks. And they want to have reproducibility along the time. I mean, 10 years or something like this. So we need to find a way to provide this solution. So we made a tailor-made distributed app stack, using the ideas of EASY and Compute Canada and other initiatives that you perfectly know. So we use the same approach, the same kind of stuff. And I will focus today in the software layer and how we distribute it. So this is a tailor-made solution. So the first thing that I think that is quite not common is that Anaconda is the main Python flavor. So we have the Python installation, and we have also an Anaconda one that is widely used by the scientists to control their environments using Conda environments. And Anaconda provides us supported Python distribution and accurate set of packages. So for this kind of companies, they want someone to guarantee that the software is well compiled, and someone to protect them in such a way. So we decide to provide Python and Anaconda, so the users can choose one to use, but all the applications are built on top of all the applications that need Python are built on top of Anaconda. So it sounds not a good idea, and we have a lot of headaches with in particular with applications that are compiled with CMake. CMake resolve all the dependencies to the Anaconda, and we have to figure out things to fix it. We also have to make changes on the easy blocks related with Python applications. So this was a lot of job, and also in the easy configs. So once we decide the Python stuff, we have two ways to provide applications. We develop a couple of workflows to do that. So we have a testing workflow and a production one. All these things are working in GitLab. So all the processes start with a user request. User open a ticket in the GitLab platform or in the ticket platform that we use, requesting a software. Then one of the contributors, that are almost 10 contributors, open a merge request. This merge request could only have the name of the applications using the EasyBuild, EasyConfigs base, or with this merge request can also contain a customized EasyConfig or an EasyHook or whatever that they need to provide. We built locally using but as I commented maybe 2 days ago, we used 2 architectures, the top one and the lower level one that can be used everywhere, and we distributed. So this is locally built in a cluster, so this is distributed using the shared storage in the cluster, and outside the cluster with via CVMFS. And finally, the user tested. So once the user tested, if the state is okay, the application goes a peer review approval. This peer review approval is, well, as I told in the beginning, one of the contributors opened a request. So in this peer review approval, other reviewers, other contributors evaluate the quality of the EC config or the installation, and then it's merged to production and goes to production. With this approach, we install 200 apps and all the dependencies that they involve. So it's a lot of job that we have done here. So what about the restricted software? So I have an example here. This is now a piece of software that have a database and a license. So we divide the thing in three parts. One, the software, the license, and the database. Mainly because databases are quite frequently actualized, and also the licenses should be actualized. So if we want to install again the software, we have to make all the pack together. So we decide to divide it just for convenience. We develop GitLab workflows to do that. So each part of this restricted software goes to the CVMFS, and then it's synchronized to the final user. So at the end of the day, the final user gets all the package. In such a way, we can control, we can monitor, we can grant users access to the restricted servers, and we can control who can get access there. So we have total control of the distribution of restricted software. So with keep in mind that we have restricted software and we have general software, we use a layered approach to have to provide the user a suited app stack. So we have a common set of applications included compilers, Python, R, SnakeMake, and bioinformatica stuff, also Anaconda. And on top of that, we provide organization specific. As we told at the beginning, we have 3 organizations around the globe, so we can provide certain kind of packages for a certain kind of users. Also, we can have a set of applications that can organize restricted. So the final user gets access to a set of applications that he really needs. So in this case, we have multiple repositories to have control access to the site. Well, this is in production over a year ago. So because we need to provide this application as abstract as the production level. Lessons that we learned in this process. So legacy code. So provide legacy code is quite so hard. We spend a lot of time making patches, debugging, and just to figure out how to make it work. Precompiled applications, build it in a top of compatibility layer. So it's a mess. It's quite difficult to figure out. Each case, in one cases we modify the binaries. In another case, if we modify the binaries, it doesn't work. So it's quite difficult to figure out which is the best way. And the worst case is graphical and precompiled. So it's so hard. And finally, the user compiled. Commonly, the user compiled applications use the LD library path to resolve the dependencies. So we have to work hardly to provide some solutions for them. Future work. Well, 2 things. In the future, we can use EC as the common layer. I mean, we are actually promoting to our clients that could be a solution for them. So in the compatibility layer, instead of having the common layer in this case, we can provide EC as the common layer, and on top of that, we can build organization-specific, company-specific software to provide them. So it's a good way to provide. And also, we are part of the Multiscape project. So we can do the abstract maintenance. We have several customers that request us installation software via Easy Build and provide an Easy config or install it by hand. We can also do the training regarding Easy Build and other Easy related applications. And finally, we can do customer support. That is one of the main things that we do, and more. And that's it. Thank you.
Thanks. Any questions in the room? Or online?
Thank you. If you are building on top of the Easy layer with your custom applications, then you're using Elmod to also pull in the underlying libraries or applications that you.
Yes.
Okay.
I mean, it's like having Easy, but in a restricted environment. I mean, all the same principles that we heard here, that we have a compatibility layer, a support layer, are all the things of it.
Yeah, thank you.
That's also something we really envision that Easy can enable, like a common ground that works. If you can collaborate there, please do. But there's always going to be situations where you need to take matters into your own hands and either work with licensed software or software that cannot be made public, or installations that we do already provide, but that you want to customize for whatever reason. You just install it again in your own repository and you shadow what's in Easy, so you get the upper hand in some sense. And we think that makes a lot of sense and is actually going to be necessary. And I don't think anyone will be able to use Easy and only Easy and make everyone happy. That's going to be very difficult. So, and whether you use own custom repositories, whether you do that also with CVMFS or just with an NFS mount that relies on dependencies provided through Easy, all of that is possible.
Anyone else?
Well, a couple of things. So we have a HPC knowledge meeting, so it should be in May. It's good to know. And we are hiring. So if someone is interested, so please contact us.
We let you get started. So Hugo, sorry, over to you.
Yep. Okay. Thanks. How are we in time? It's 2 o'clock. Do you want the long version or the short version? We'll do the intermediate version. Okay. So 2 seconds about why we are actually interested in this. We're doing quite a bit nowadays with HPC at Microsoft. We are number 10 as of November with one of our systems. We have been one of the previous systems. We have actually 4 of those, which are conveniently 26, 27, 28, and 29. The reason why is that it's exactly the same systems, but we have different regions in the world where we just duplicated those systems. So yeah, that is sort of like the scale we're operating at. Also, from a large compute point of view, one of the things that Stefan just mentioned regarding very large scale NLP projects, that is actually something we do together with Meta Facebook. They have been already delivering some of the research results from that, which has been quite impressive. Also, we are building a couple of, that's not public, we are building a couple of supercomputers for the UK Met Office, which will be in production after the next year or so. Meteo is quite slow in actually bringing stuff in production. So the concept I'm always trying to think about when using Easy is sort of like this list, and this is a dynamic list with our HPC fleet of compute SKUs. So
there are two things quite interesting. On one hand, this is a very dynamic list in the sense that, yes, we're adding CPUs and GPUs to this list. And by the way, for the first time, we are actually decommissioning stuff. So that's quite interesting. The other dimension is that this list is very static. So that means that if I take an HB120v3 with Milan X, in one region, it's going to be exactly the same as in another region. So it's very sort of like predictable if you take this type of SKU anywhere in the world, where you are going to land on. So those two dimensions are interesting when using HPC in this environment. Yep, we have data centers. We have, so these are actually normal, what you would expect SKUs. In this case, I believe this is the Milan. So just two sockets, two-socket machine with an InfiniBand connector. So whenever you have a VM like this, you're actually landing on for the HPC SKU. The CPU SKUs, you're always landing on a complete machine. GPU machines, it depends a little bit on which of the versions. So the first few, you can actually get partial machines with 1 or 2, or the complete 4 GPUs. With the larger SKUs, you're always landing on a machine. It doesn't make sense for this one to split it up, because here you can have the one GPU version. Okay, so doing application delivery, this is one of the big challenges that we do like to think about, because we want to help and enable the customer a little bit further than just saying, yep, here's the infrastructure as a service, go spin up your own image, have fun. We do recognize that when a customer tries to do HPC in Azure, they actually sort of like assume that we are going to be their HPC admin as well. Depends a little bit of the size of the customer, but a lot of the questions, even coming from sort of like the very large HPC, tend to work with some of the larger customers in this field. They do come with questions where they sort of like assume, oh, but you're taking over part of our work because you're now the supplier, so you're taking care of all of that. It's a good thing on one hand. It's a little bit tricky on the other hand, and especially regarding applications, it's very tricky, which you might already know that. I don't trust that. Okay. So it's a little bit tricky, and definitely we want to look for a solution there. We've been trying it multiple times already. Either built on CVMFS using EasyBuild and with spec, and going through RPMs and stuff like that. We don't feel comfortable yet with releasing that, and basically I tend to sort of like completely stop that progress and transfer our efforts completely into Easy. It won't be completely possible because Easy doesn't support commercial software from ISVs and stuff like that yet. So we still have a sort of like a gap to close, but moving forward, we really like the Easy stack. And basically what we're doing today is we have the Easy stack, the pilot version, integrated in our AC Hub delivery model today. We have been using it already, as I will show later on. But we do have a couple of gaps there. One is CPU detection, which may be a little bit Azure specific. GPU enablement, well, we have been discussing it about that, and I hope to help progressing that as well. And the end-to-end runs, basically discussed with using the testing framework as well. So this is a slide I stole from the CVMFS meeting. So it's not the upcoming hackathon, actually we're doing it now, so that's good. Like I said, Easy Client is enabled. This is now not thing. This one was interesting. This is one of the issues we encountered when running on InfiniBand on Azure with the 2028 version software stack. We had to enable UCX as being the primary libfabric loader. After that, you get nice low latency with RDMA. Well, TCP, you know about it. This is sort of like the things we try to focus on and validate and highlight and improve. And I think this is sort of kind of feedback you are going to get from on which we should be trying to like make the software work for everyone. This is going to be difficult because what happens if there's NLPL or Rocky? So this is not.
Yeah, so I think this particular export is not necessary for 20 whatever the 21 toolchain that's in there.
So specifically for OpenMPI 4.1, it's not no longer necessary. So this is fixed.
But you're right. You're right. I mean, and also OpenMPI is doing checking, right? That you could sidestep, right? I mean, whenever it starts up, it's checking the connections that you have to find the right one.
Yeah.
You can tell it, don't bother doing that. I know the answer. I mean,
yeah, but then you have to do this at the job script level.
Like this, you have to like export a very.
Yeah.
I mean, we did discuss this idea of having kind of a semi-visible dependency in the OpenMPI module, which is like that kind of configuration stuff. You are likely to need more environment variables to really tune the for your particular use case. And that's probably true of multiple things, right? Also UCX, also...
We have to encounter this. Yeah.
So there are likely to be some kind of site configuration stuff. And now we actually, with the host injections thing, have a way of straightforward to do, actually.
Awesome. So this is one of the talks we did where we were using Easy for doing warp simulations. That went down pretty well. So yep, we are also very public and vocal about doing this. On that, one of the things, apart from the repeated one, so it's 4.1. There's another one which was a little bit tricky for us, and that was the detection of the Zen3. That is something where actually this week has been quite productive. I wrote a little script that sort of like tries to replicate the function of argspec. I conveniently called it argdetect. Basically, it works now on paper. So doing the testing, it works on all the architectures. I don't know in practice yet, because we should be putting it into sort of like a beta version of the OS, and let's see if it works. It's not enabled by default. So I think the merge is safe. Set up an environment variable, then this one will to like validate what's going on. Sorry? Yes. So we can also move away from the Python. It was quite heavy. Yeah. It's we're having discussions of whether the abstraction level within the shell script is good enough, but we'll see. Any more? Yeah. One thing we did in here, which is a little bit tricky and breaking compatibility with argspec, is that we introduce support for the ARM Neoverse N1, not in argspec. And actually, this one is an old one because we already removed Grafton 2 and Grafton 3. With the assumption that Grafton 2 and Grafton 3 are actually implementations of the Neoverse N1 and the N1. So for compatibility reasons, we are proposal is to make symlinks from Grafton 2 to Neoverse N1 and from Grafton 3 into Neoverse. Complete compatibility, but yep, like improved abstraction naming. Yeah, well, I was forced to by Kenneth. Step further about CVMFS work and strategy networks and stuff like that. Originally, CVMFS has support for S3. S3 is not Azure Blob. There are some subtle differences in when you upload Blob. On the Azure side, we do need a little bit more information within the request. So I coded that into the CVMFS server. That has been in there since 7.8, I believe. We are now at 2.9, so it has been in there for a little while. And that means that the CVMFS server can build on a Stratum 1 today directly on Azure Blob. So that means that we can run CVMFS completely as a SaaS PaaS only requiring a storage blob. I don't need any VM anymore. I can just push it into a storage blob, delete everything else, and it runs. And that means I can do some other tricks as well. And one of the tricks I've been playing with is creating a global traffic manager and then pointing to worldwide storage accounts in different regions in the world and sort of like having global low latency towards, so that's called Stratum 2 network. So having global low latency access into the CVMFS repositories with a load of bandwidth. So this is one of the things I want to try if I can a little bit further. One of the things I want to do is set up a Stratum 1 that is based on Azure Blob that presents itself as a single Stratum 1, but underneath will support all the 50 regions within Azure with direct low latency Stratum 1 so that people don't have to set up a squid and anything. Just sort of like free there for them to use. Bandwidth, low latency. Still work in progress, but that's fun. The other thing is that this week I was able to verify that this system also HTTPS, and to make sure that keeps working, I also added an Azure Write test into the CVMFS code base. Still needs to be merged, but make sure that it keeps working. Next steps that I'm planning, extending the work on Easy. My focus will be mostly WRF and molecular dynamics. One of the things we want to do is now that it is moving sort of like it has an outlook towards production environment, we want to double down on it, make sure that we have properly documented scenarios for users, including submission scripts in Term and PPS, including sort of like demonstrated benchmarks with optimized NUMA placements, stuff like that. We can do that because we know where we are landing. And with that, also make sure that that is not by reframe, so that we can actually do regression tests on our systems. That is definitely one of the benefits that I'm getting out of it. We can do regression testing on our system, and we know what it should be if stuff like a hypervisor layer changes or security scripts that are running on that hypervisor are changing the impact on the HPC. This is one of the discussions I spent last year, quite a bit of work into getting Azure enabled from ITC perspective. Unfortunately, that hasn't been picked up by the ITC maintainer. The Rs are in there, it has been picked up. I push through on that, switch to Magic Castle. I mean, let's keep that as an open discussion, but I do like some feedback on that. Container deployments, we'll be using some of the containers in a CVS-based register, because the speed up of that is apparently towards what we learned from the CVS. Should that become a part of Easy? I don't know. Let's discuss later on this one. And yeah, happy to discuss also about these. So that's it for me.
I think the serverless thing is really interesting for the CI stuff, right? So if the serverless stuff inside the GitHub and everything, right, so that we keep all the traffic in there, is really interesting.
Yeah.
One thing I was wondering about the HTTPS, does that mean then that you could use JWTs, like tokens for access, like sort of strict access based on something?
No, because this is only providing encryption at the transport layer. But these tests in the client code, I'm not aware of anything that can do. Well, I don't know about the compatibility between JWT tests at the moment. So maybe, but that is definitely not why I did this. Why I did this is because you need to explicitly enable HTTP only in Azure Blob. And my first reaction that was, oh, we're going to have issues with security teams from customers when you have to do it. And this sort of like takes it off.
So with the Stratum ones, the idea that you would then, like if a customer in Azure uses Easy, would it always pick it up from the Stratum ones that you have in the Azure blobs? Is that the idea? And does that mean that you alter the configuration for Easy? Or do you rely on the Geo API to just say, no, this is always the closest one, wherever you are?
I don't know yet. Oh, open for discussion.
Yeah. No, because I can imagine the Geo API will probably say, because it's one location, right? It presents itself as one Stratum 1.
So the Geo API will probably say, I'm picking up this one, because that is like the closest one. It may pick up this one. I haven't tested.
Yeah.
That being said, I mean, for the, it doesn't say here, for the AC Hub, we are in control of the configuration, or sort of like we provide an initial one. Yeah, let's see. That one I can point easily, make sure that it's only picking up the Azure ones.
Yeah.
The other one.
In our GitHub Action plugin thing, we also control the configuration, right?
Yeah.
So we can just say point to that one, and that's it.
Yeah,
it's done.